Okay, good morning and welcome everybody. It's a great pleasure to have Matt Headrick, and he will continue with his series of lectures on entanglement aspects of AdS CFT.
So thanks to all of you for getting up early and coming back to see me again this morning. So in the last lecture, I just talked in general terms about entanglement entropy, why it's called that, and some of its properties. And today what we're going to do is talk about, more specifically, entanglement entropy in quantum field theories. And maybe I can make a quick remark relating this to Tom Faulkner's lectures, which are also about field theories. And you'll notice a difference in approach. So he hasn't talked about entropies yet. I assume he will. But what he's doing is, so for example, he said at the end of his lecture that if you have a quantum field theory and you look at a region of it, which is also what we're going to do today, it has the algebra associated to that is a type 3 von Neumann algebra, which is a very scary, wild kind of algebra that doesn't have projectors, it doesn't have finite projectors, doesn't really have states in the usual sense, and so it doesn't have density matrices in the usual sense. So how can it have an entropy if the entropy is minus trace rho log rho and there's no rho? Whereas in my lecture today, we're going to be calculating minus trace rho log rho the entire lecture. So you might think that there's some clash there. And the point is that he's working directly in the continuum, and I'm not. So in order to get a minus trace rho log rho, in order to get a rho, in order to get a density matrix for my region, so in order to get more specifically a rho sub A, so for me, A would be some spatial region living, as I mentioned last time, so this is the blackboard is a Cauchy slice, and A is some spatial region. And in order to get a rho sub A, I'm going to need a cutoff. And Tom is simply working in a framework in which the cutoff is not there. It's a purely continuum quantum field theory. The same issue would arise, the same issue arises when you do perturbation theory. If you calculate loop diagrams in the usual textbook way, you need, those loop diagrams contain ultraviolet divergences, and you need to cut them off. You need to regulate them by introducing an ultraviolet regulator. And then after you do some work and you renormalize and so on, you can calculate a quantity which is not dependent on the UV regulator, and which would be the actual observed quantity, some S matrix element. And so it's the calculational method that requires the introduction at an intermediate step of a regulator. We will also calculate regulator independent quantities, and in Tom's approach, those are just the only quantities that are defined, okay? So I hope that's clear. It's the same as when you learn perturbation theory and you introduce a regulator. We're doing the same thing, okay? Okay, so I mean, that being said, there's an incredible amount of interesting physics contained in the specifics of regulators and how you regulate different ways of regulating quantum field theories, different ways of regulating entanglement entropies, and that is itself quite an interesting subject, which I'm going to be very glib about. So what I did last time is I did a simple regulator, simple ultraviolet regulator, where I took my continuum and I replaced it with a lattice, a finely spaced lattice of points, and I said that there's some maybe spins at each point. And then when I do that, so when there's some distance separating the points, and I argued that the dominant contribution to the entanglement entropy would be due to basically breaking nearest neighbor bonds, and the number of those nearest neighbor bonds is proportional to the area of the entangling surface. Just get this terminology on the board. In units of the cutoff. So that's one kind of simple regulator that you can use. It's a bit of an ugly regulator because it introduces some anisotropy and so on that we're not necessarily interested in if we're really interested in what happens in the continuum. Okay, so today I'm going to discuss a different way of getting at the leading term in the entanglement entropy, which instead goes to what we learned actually a couple of days ago from Raju, which is what is the state of Rindler space? Okay. So what I had done before is so the lattice regulator suggests S of A is equal to something which depends on the area of the entangling surface in units of epsilon to the d minus 1. For me, d throughout these lectures is equal to the number of spatial dimensions. Oh, I forgot to, somebody asked me for references. So basically my lectures are following lecture notes that I wrote several years ago that you can find on the archive. So, and the references are in there, historical references and so on. Okay, so, and the point that I made at the end of yesterday's lecture is that from the point of view of the maximum possible entanglement for the set of spins that are contained within this region, this is actually a very small amount of entanglement. So the maximum, so the max possible S of A is like, it goes like the volume of A in units of epsilon to the D. And so because of the dynamics, because we assume that the Hamiltonian is local, because we assume that the physics is local, and that therefore that most of the entanglement occurs across the entangling surface, the amount of entanglement is very small. Now, that being said, somebody asked me, I think afterwards, what if there is, what if you're at finite temperature, and then isn't there an entropy that goes like the volume? So we know that entropy is an extensive thermodynamic quantity, and so in general, if you have some system, at least in a thermodynamic limit, which is at finite temperature, it'll have some finite entropy density, and therefore the total entropy will be proportional to the volume of the system. And so indeed, so this is not the entire entropy by any means. This is just one part of the entropy. There's going to be lots of other parts that depend on lots of specifics of the theory, the state, and the region we chose. And one of those terms may be, if you're at finite temperature, indeed proportional to the volume. Okay, where this is the entropy density. Thermal entropy density. And so that guy will be proportional to the volume, okay? But this is still true because while these things are both proportional to the volume, this one is proportional to, is in units of the cutoff. And this is the maximum possible entropy density, whereas the thermal entropy density will be always much less than that if you're in a regime where you are indeed modeling your field theory by the lattice. Okay, so you need T much less than 1 over epsilon. So 1 over epsilon is some kind of energy scale associated with my UV regulator. If my temperature is anywhere close to this, the inverse lattice spacing, I'm really not doing a field theory. Okay, then I'm really not, that's some extremely high energy state where my energy density is close to my ultraviolet regulator scale, and you're not doing effective quantum field theory anymore. Okay, if you don't obey this requirement. Sorry for my cluttered board work. Let me see if I can. Okay, so we need T much less than 1 over epsilon. Okay, so that's just to say that indeed there can be a volume term. Nonetheless, the entropy is still much less than the maximum. It's still highly unentangled. Okay?
Matt, I have a question. Hi.
Yeah.
Suppose you have next to nearest neighbor interactions. Then what do you do?
Yeah, so I mean, this is just schematic. So, so there will be entanglement beyond just, I mean, actually, let me just back up and say that the cartoon I presented where I'm calculating the entanglement entropy by adding up contributions, is already too crude because entropy just doesn't work that way. It's not true in general that the entanglement entropies can be written just as a sum of a contribution from this bond and a contribution from this bond and so on. So that was just to get an estimate. And so all I need is some form of locality. If I don't have any form of locality, if the way that I've drawn the lattice on the blackboard is actually irrelevant and everything is interacting with everything else equally, then you will get this kind of entanglement entropy. But as long as you have some kind of locality, you should get something that somehow depends on this surface area. Yeah. Yes. Well, that'll actually sort of depend on parameters because they just have different parametric dependencies. So even if we satisfy this requirement, if you make the region large enough, it could happen that this is actually larger than this for fixed cutoff. But really, I mean, it sort of gets a little bit, if you're being careful, okay, if you're really being careful with your order of limits, what you should do is you should, fix the space, fix the region, and then take epsilon smaller than anything else going on, and then indeed this will be larger than this. But it's not really necessary to do that because they have different parametric dependencies. So you can they're kind of separate terms in a way, yeah. Okay, that's a good point. So, in fact, this, the fact that you get this leading area term, of course, it's not true for every state. There exist unentangled states. But those states are very far from the ground state. So basically, the way we have to think about it if we're trying to model a field theory with a lattice is that hopefully if it's a good model, so the lattice will have some spectrum of states, and the low-lying states, basically those with energy density satisfying this, are modeling field theory states. Okay, so their physics is close to that of the field theory states. Then there's a huge amount of crap, which is just due to the fact that you have a lattice, okay? And the states that violate this are up there, okay? So if you try to unentangle A from its complement by picking some state where there's actually very little entanglement across the cut, that state will have a huge energy density in this region, okay? And so it will not actually model any field theory state, okay? So in the limit that you take epsilon to 0, the energy density of that state near the cut will go to infinity, okay? It will not stay in the set of states that are modeling the field theory states, okay? So, yeah, so if I talk about, let's say, the energy density, or maybe the maximum energy density, and if we normalize things so that the vacuum has 0 energy density, and then there's some 1 over epsilon, I guess, to the d minus 1, to the d plus 1, if it's an energy density. And basically, there's some set of states down here that are modeling good QFT states. Okay? And anything in here, which would include a thermal state obeying the temperature much less than 1 over epsilon, will be in this regime. Anything in here will have S of A equals this thing I wrote. And stuff up here may be unentangled. Okay? Any other questions before I go to Rindler space?
Hello?
Yeah.
So for states like evaporating black hole, at the late time, the volume law will be dominant than the area law because the temperature is increasing.
Wait, say that again for states like what?
Evaporating black holes.
An evaporating black hole, okay.
So at late times, the temperature will be large. So the volume law will be followed by entanglement entropy than area.
Right, so I was going to talk about what happens when you have gravity in a little bit, but let me just let me just say, since you brought it up, that if you're doing semi-classical gravity, then what I'm saying holds there. So you have quantum fields that are fluctuating on a space-time background that is mildly fluctuating, that has its own fluctuations, which are the quantum fluctuations of the graviton field. But you're not talking about large fluctuations of the space-time background. So you're just doing semi-classical, maybe perturbative quantum gravity. Then what I'm saying holds. But of course, in that case, the cutoff that you use should be larger than the Planck length. So everything is fine until the black hole is comparable to the Planck size. And at that point, of course, quantum field theory is no longer a good description. Semi-classical gravity is no longer a good description. And you better have a different description. But what I'm saying is valid as long as the black hole is nice and big compared to the Planck length. Yeah. So I'll return to that quantum gravity thing in a few minutes. Yes?
So what you just said is that we have a good description only when we have very low line states. So if I want to take a thermal system, we can all the states for a partition function. This description wouldn't be really accurate. But if I think of a CFT and I go to a cylinder with the there, I'm actually describing the thermal state, and if I can put entanglement entropy, I get the volumetric contribution to be the dominant one of the large temperature. So how does that picture connect to the argument you just said?
Well, so in the case of the so we'll do the conformal field theory, but I mean, it's always true. You could always object that we really can't do thermodynamics, or we really can't talk about a Gibbs state or a canonical ensemble for any physical system because we don't know what the system looks like at extremely high energies, and the Gibbs state includes a sum over very high energies, right? In principle, you're supposed to sum over all energies. So if I have gas in a box, it's hopeless because what happens when the gas has, is when the gas molecules have a kinetic energy which is large enough to do particle creation, and then I need to actually model it in terms of the standard model, so we can't do a gas in a box until we know the standard model. Well, of course, that's not true because you have an exponential suppression, and so hopefully it doesn't matter for a gas at room temperature, nuclear physics doesn't really enter if you want to model that, right? And so I'm just doing the same thing. So while it's true, so if this is an energy density, and then it's true that at finite temperature, I need to integrate over all of these, and that means including all kinds of states that I've said are bad. As long as this condition is obeyed, those states kind of don't matter. Okay, so in practice, you're really only, as long as this condition is obeyed, by the time you get to the top of this band, the exponential suppression is so large that it really doesn't matter what happens there. So you can use a lattice to model, even though you're getting the ultraviolet wrong, even though the deep ultraviolet of the lattice is different from the deep ultraviolet of some other system, it doesn't matter as long as the temperature is much less than that. Is that okay? Okay. Great. Lots of great questions. Lattice is super awkward. It's good for doing numerics, and it's good for conceptual things where you really don't get too confused because it's just a finite, set of maybe large but finite set of spins or something like that. But it's kind of ugly. It breaks, your nice space-time, continuous space-time symmetries. So you might not be entirely confident, or you might not be entirely convinced by my argument here, especially if you study it a little bit more carefully. The number of bonds that are broken, if let's say I have a square lattice in 2 dimensions, is not really proportional to the area because it kind of depends in some complicated way on the angle of the entangling surface and so on. So you might actually doubt that. So I'll give you a different argument, which also I think is sort of maybe more field theory-like, which is instead of a lattice, we can model the region near the entangling surface by Rindler space. Which thankfully we've already learned about. Okay, so you just say, well, as long as the entangling surface is smooth, so this is assuming the entangling surface is smooth, and one can consider things that have sharp corners, and then those are very interesting, and they have interesting physics, which is not what I'm about to describe, which can also be studied, which has also been studied. So assuming the entangling surface is smooth, we can zoom in on a part of it, and as long as that part is small, so we don't see that it's curved and so on, it basically looks flat, okay? And we know a lot about Rindler space, because we were taught a lot about Rindler space just yesterday. Rindler space, you have a temperature. So Rindler space, the vacuum, is equal to a thermal state. Are you guys hearing that echo? It's just me? Okay, I'm gonna lower this a little bit. I'm hearing like a reverberation. Can you still hear me like that, or it's still clear? Okay. Thermal state at temperature 2 pi with respect to the boost generator. Okay, so now I'm really assuming that I have a relativistic quantum field theory, so this is actually a piece of space. So there's a time direction, and when I approach the entangling surface, I can really think of that as Rindler space, and as in Rindler space, you throw out half of your space, this half on one side of some plane, and that's what I'm doing here, okay? Now, so I have my boost generator K, and now the thing is, so this is a constant temperature. So Rindler space is in thermal equilibrium. It's in the canonical ensemble at a fixed temperature, where the Hamiltonian is the boost generator. And that is what will be measured by an observer. So in Rindler space, so this is one of my directions. Observers who stay inside Rindler space have to accelerate to stay inside Rindler space. The simplest ones are stay at fixed proper distance from the origin. Okay. And as a result, this observer will, for example, see a bath of particles. If let's say if it's a free quantum field theory, they'll observe a bath of particles, and that's the Unruh effect. But you see that if you ask, well, what is the temperature of that bath of particles? The answer 2 pi isn't very satisfying because it has the wrong units. And the reason the temperature has the wrong units is that my boost generator has the wrong units, okay? And the physical temperature, actually, what you have to do is you have to convert it by looking at the norm of the time-like vector field that generates the boosts, okay? And that gives you the physical temperature seen by the observer, okay? So an observer, so let's say, so an observer, well, a Rindler observer, meaning one who is accelerating, at, let's say, t equals 0, sees a bath at t phys, which is basically 1 over x1. There's some 2 pi in there, but I'm not going to pay attention to those because I'm just doing an estimate, okay? So this is the physical temperature observed by this observer, and you see why there's an entropy. And you also see why that entropy is divergent, okay? So basically, the different observers see different temperatures, and if you're far from the cut, this is my cut, this is my model of, is this point, right? Because the other directions are coming out of the board. So if you're far from that entangling surface, then you're chill, right? The temperature is low, okay? You don't see anything exciting happening. As you get closer and closer, it gets hotter and hotter. So very close to the entangling surface, it's very, very hot there, okay? I just want to emphasize that this is not some formal mumbo jumbo. Like this observer literally detects particles, literally is living in a very, very hot bath. And the closer they are to this point, the hotter the bath, okay? So of course, since they're in a thermal bath, there's an entropy density, okay? And the closer they are, the higher the entropy density, and that's where the UV divergence comes from, okay? So what we're gonna get for the entropy density, is just, well, you're going to get some entropy density, which depends on the theory, right? There's some equation of state that determines the entropy density as a function of the temperature, okay? And what you want to do, so S of A, then, is going to be an integral over the other directions, so over entangling surface, of the other directions, x2 to xd. So that's the integral in this direction. And then an integral over x1 s of t. And t here is 1 over x1. Okay? Yeah, so what I'm saying is the entanglement entropy is a thermal entropy that has been integrated. So it's the thermal entropy due to the Unruh effect that has been integrated up to the entangling surface. So this thing is from 0 up to some distance, so which depends basically on the size. So you wouldn't, of course, this is sort of a little, this is just an estimate where I'm kind of assuming that this is smooth. And so I'm zooming in, and I'm not worrying too much about, there also may be entanglement, you know, in here. So maybe up to some, maybe we look at some band just to estimate it. And we put this distance as LIR. So from 0 up to some LIR. So we cut it off. And this would just be the leading term. But anyway, to answer your question, my claim is that the entanglement entropy in the vacuum, or any low-lying state, because in any low-lying state, it looks like, if you zoom in sufficiently close, it looks like Rindler space in the vacuum, can be expressed in this way, as an integral of a thermal entropy. Okay? Yes?
Why the observers near the entangling surface, you are approximating it to some Rindler observers? Why is that the case?
So it's very important for the physics of Rindler space that you restrict yourself to observers who stay within Rindler space, right? An observer who's just staying put or traveling at finite speed with respect to the Minkowski coordinates does not see any thermal bath of particles, okay? But here, what we're talking about is, and maybe I should have made it clear that this is the A side, and this is the A complement side, okay? So everything in here is A on the t equals 0 slice. And I'm getting the entanglement entropy by asking observers who live in Rindler space, that is, who live in the causal domain of A, what entropy density they are detecting and adding that up. Okay?
The surface is just entangling surface, right? There is no such such things as horizon. Horizon in the sense Rindler horizon, right? When you are calculating entanglement entropy.
Sorry, maybe I should make, I mean, so if I take this picture and I add the time direction, then it looks like this. So there's, right? So the causal domain of this thing has a null hypersurface coming out, and then to the future and to the past, okay? And the causal domain looks like this. I mean, in cross section, it looks just like that. Let me draw it. Let me attempt one more drawing that might help. So this is my region A, and here's its causal domain, okay? And near, let's say, this point, okay, even though, okay, there's some, you know, A is some complicated thing, but near this point, it looks just like this figure. Okay, so as long as you zoom in, the causal domain of A looks just like Rindler space. Okay, and the entanglement entropy is just the Rindler, and is just the entropy of Rindler space. Okay? I mean, I want to emphasize it's a real physical entropy. Yeah.
Could you give some understanding for why the normal entropy can give you the entanglement entropy?
Because they're just the same thing. I mean, so let's say, okay, I just have, I mean, don't worry about the fact that the system, the field theory reduced to A, came from a field theory. It's just some finite size system that's hot. Okay? Now, there's a subtlety here, which I sort of swept under the rug, which is that the temperature is position dependent. And so from this point of view, it seems like the system is not in thermal equilibrium. And so it's definitely true that if you have a system with a position varying temperature, then this is a slightly dodgy way to calculate the total entropy. So this is only really going to give us an estimate. Okay, so this is really just going to give us the parametric dependence on the size of the system. Okay, it's not really correct to calculate an entropy if you have a position dependent temperature by just integrating up the entropy density. Okay, the full entropy is more complicated than that, but that's going to be okay in this case because the effect is so dramatic. Because what's going to happen is that this temperature goes to infinity, and therefore to get the parametric dependence, it's enough just to do this integral. Okay.
So I guess it's like near these ringlet horizons, you're thinking that both the sides have like in thermal state with same temperature, and therefore the entanglement entropy will be given by the thermal entropy.
Well, I'm only looking at one side. I'm not worrying about what happens on this side. Just looking at the A side. Okay? So the A side is some system that has a position-dependent temperature where that temperature is going to infinity as you approach its boundary. Okay? Okay, so let's go ahead and do this integral. So we have to know something about this function. And of course, this function depends on the what field theory we're talking about. But what is true is that as long as your field theory has some ultraviolet fixed point, because what happens as you approach the entangling surface is it gets hotter and hotter and hotter. Okay, and so if your theory has an ultraviolet fixed point, then the entropy density at that fixed point has a very simple dependence on the temperature. Okay, so let me write that over here. So as x1 goes to 0, t goes to infinity. So if the theory has a UV fixed point, then S of t is proportional to whatever you get from dimensional analysis, because at a fixed point, there's no other scales. So the theory may be a massive theory, let's say it, so let's say the theory is a massive theory. In the ultraviolet, the mass is irrelevant, and so you can calculate the entropy density without knowing the mass, okay? And it's just determined by dimensional analysis where all you have is the temperature. And since all you have is the temperature, and this S, since it's a density of a dimensionless quantity, has units of length to the minus d, this is proportional to t to the minus d, okay, by dimensional analysis. Okay, so we get S of A. So this first integral is going to give us the area of the entangling surface. Times the integral from 0 to our IR cutoff. dx1. Meanwhile, oh, I'm sorry, you guys allowed me to, there's a mistake on the board. Where's the mistake? This thing has units of 1 over length, so, and of course, obviously, at high temperature, the entropy density should increase, so it's a positive power. So I get 1 over x1 to the d. Okay? And there's our UV divergence, because this integral doesn't converge. Okay? And so I better introduce a cutoff, so I'm going to make this to my UV cutoff scale. Okay? And that's the origin of the divergence from this viewpoint. And you get exactly what I said. You get okay. Okay, so all of this was just to give you a different derivation of the same result. Again, there are clearly corrections from many places here. One correction is because I kind of put in this arbitrary IR cutoff that I then didn't deal with. Another correction is from the fact that this is really not true, that you can get the entropy just by integrating up a local entropy density. Another correction is from the fact that it's not, the entangling surface is not really flat, it has curvature, so on and so forth, okay? And obviously the state dependence should enter somewhere and so on. So this, the state dependence will be in here, the dependence on the curvature of the entangling surface will be here, and so on and so forth. The dependence on the theory. There is a dependence on the theory here that I didn't, that I could have mentioned, which is that this coefficient already depends on the UV fixed point. It depends on the number of degrees of freedom of the UV fixed point. So you can already, if you're just doing this a little more carefully than the way I did it, you can already learn something about the coefficient here. Okay? Okay. Any questions about that? Yes, Ashok?
Suppose you are doing this calculation in a string, right? And here you know that the entropy density will be affected by an iron density and another black hole. So could we make use of this to try to see what happens to entanglement entropy?
Yeah, so I mean, that is essentially the program that like Atish has been pursuing. In fact, let me,
We are using the replica trick, but it doesn't seem to use replica trick at all.
no, he's definitely using the replica trick.
Why are you using replica trick?
Oh no, I'm, right. You're saying he's using the replica trick and I'm not. Oh, let me, to bring everybody else into the conversation, just mention the replica trick in this setting. Because the replica trick calculation proceeds by computing trace rho to the alpha, if you recall. And how do you compute this in a, let's say for Rindler space or for our situation? Well, you have to write down what the state is. So if you're doing the vacuum, you get the vacuum state by doing a path integral over, let's say, the lower half plane. So this is my Euclidean time direction. And this is my x1, and I have the other directions. And then rho sub A, so this is my vacuum state. And this, the dual state is this path integral, okay? Where basically what you're computing, so this is just the entire half space down here. And basically what you're computing is the wave functional of the wave function. If you want to know the, for some given field configuration at t equals 0, you want to know what is the overlap of that with the vacuum state, is that you set a boundary condition phi of x here, and then you do the path integral over the half space with this boundary condition. And then you say, well, actually what I'm interested in is, so only part of this space is A. So I have something like that, where this part is A. And you trace over the complement. So to get rho sub A, you set this equal to this, and then integrate over all possible values. And that's the trace over A complement. So this is A, and this is A complement, okay? And rho sub A is given by just gluing this to this. So you're doing this path integral over everything up to the entangling surface. And then you have to compute, like the second Renyi, you want to compute trace rho sub A squared. So you take 2 copies of this and then glue it to itself. So you would have something like this. 2 copies. Okay, and you glue like this top thing to this bottom thing, and this bottom thing to this top thing, and you get this 2-sheeted, basically Riemann surface. Okay, I mean there's extra dimensions here that I'm not drawing, but the point is that so then what you can calculate the Euclidean partition function on this 2-sheeted thing, and the 2-sheeted thing has a conical singularity at the entangling surface, because just like for a Riemann surface, let's say the Riemann surface for the function square root of z has 2 sheets, okay, and when you go around, you have to go around the origin twice to get back to where you started, which means that the angle, the total angle around the origin is not 2 pi but 4 pi, so you have a conical singularity there. So there's a conical singularity. So this is, for example, trace rho A squared is given by this. So this has a conical singularity with angle 2 pi alpha. So this case was alpha equals 2. But you can see that if I did the 3-sheeted thing, I would get 6 pi and so on at the entangling surface. This, when you could compute the partition function of a field theory on a space with a conical singularity, there's a divergence associated with that singularity. You get infinity, which you have to regulate, and you regulate it by basically cutting out the entangling surface and replacing this conical singularity with something smooth on a scale epsilon. So you smooth out the singularity, and you replace it with something smooth, but that's of size epsilon. And as you take epsilon to 0, you recover the singularity, you recover the divergence. And so you can see from that point of view also, I didn't do the calculation, so you'll have to believe me, that this conical singularity leads to precisely this divergence. Okay, so this is just to say that how you get this stuff from the replica trick. Now in string theory, so you know, in some sense, string theory is just a fancy regulator, where the you know, instead of point particles, you have strings, and therefore, in the deep ultraviolet, the nature of the theory changes, and it ceases to be just a regular quantum field theory, and you can calculate things about it. So basically, the size of the string plays the role of epsilon in what I'm doing. That's the size at which it's can no longer be considered a regular quantum field theory. And so you can do this whole replica trick calculation in string theory and recover this result where epsilon is replaced by the size of a string. Now, Ashok's question was whether you could do, I mean, that's an honest string theory calculation. What happens is that strings, they're okay actually propagating on a space with a conical singularity. And so, yeah, everything works out nicely. Everything can be computed in string theory, at least if you're super smart, like Atish Davolkar, who's been working on this kind of thing. Why didn't Atish just do what I did here? And I think it's probably just too crude. I don't think you would, I don't think this calculation is trustworthy enough because you're in a situation from the Rindler space point of view where your temperature is varying very rapidly on a very short distance scale, on a distance scale that's comparable to the string length in terms of the regime you're interested in. And I just don't, I just don't think you can, I don't think in string theory on lengths smaller than the string length, you can think of the entropy in this very naive terms. You can think of it up to the string length, and so, yeah, parametrically you'll get the same answer, but if you actually want the answer in string theory, not just the parametric dependence, I don't think you can trust this calculation. That's my answer to that.
Is this just regular string theory with its target space that is regular space? And that target space is that target space really satisfies conditions for being normal theory? So it's a non-trivial CFT.
Yeah, that's, I think that's essentially what Atish is doing, but if you want to make quantitative statements and actually evaluate the entropy in Rindler space, I think you go to the replica trick. At least that would be the standard way to do it. There might be other ways to do it. I'm not saying there aren't. But yes, a string propagating on Rindler space is a very happy string. It's a perfectly good string background. Yes?
Are you suggesting that there would be no such area term in string theory?
No, there is.
There is.
Yeah.
But there would be no such conical singularity, right?
No, there's a conical singularity, but it's just the strings kind of don't mind the conical singularity so much, so it's well-defined. So they kind of regulate it. They kind of regulate themselves, but you still get the area term.
But this area term is is coming because of some regulator, right?
String theory is a regulator. Okay, you should think of it that way. String theory basically is a regulator for quantum field theory. So it in perturbation theory, your UV divergences are naturally cut off. But it's not that, conceptually, it's no different from having a lattice. You would say, oh, a lattice doesn't have UV divergences because you've removed them, because it is a regulator. So string theory is the same.
That regulator where you don't have any divergences, right?
Because you've removed them. Because the nature of the theory has removed that part of the phase space that gave you trouble, that gave you the infinities. Okay, so strings. Yeah, it's the same as with a lattice, you wouldn't get a divergence because the lattice has removed the divergence. In string theory, you don't get a divergence because the strings have removed the divergence. It's really exactly the same from at that concept cartoon level. Yeah. Yes. Yeah. And so this is really to sort of better justify, I just claimed here that this is what you would expect. When you have a lattice theory that does not have a continuum limit that's a relativistic quantum field theory, you can actually get all kinds of other behavior. So this is not really very trustworthy at the level at which I presented it. This is actually much more trustworthy, and it relies, as Shumet emphasizes, on the fact that we have a relativistic. So if you have a non-relativistic quantum field theory, all kinds of stuff can happen with the entanglement entropy that's different from this behavior. Actually, yes. Yeah. Yeah. So string theory has an infinite tower of, I'm going to give you a qualitative answer because I don't quite remember the quantitative answer in this case, but maybe Ashok or somebody does. But basically, so you might worry that because in string theory, actually, you have an infinite tower of string fields. But the thing is that those are, their masses are inversely proportional to the string length. And so they don't actually contribute, you don't get an infinity from that because the cutoff is already happening at the string length. So you get I think you get you get an actual number here. So this is replaced by the string length, and then there's an actual honest number, which is unambiguous. But it's not infinite. Because all those other string fields, basically, they don't, by the time this cutoff is in place, they don't ruin it for you. It's the same thing that in string theory, if you do like a one-loop calculation, you might worry that actually the situation is terrible because before you just had like a scalar field running in a loop, and now you have an infinite number of fields running in a loop, so don't you get a worse divergence. But in fact, that it sort of gets cut off before those other fields can contribute an infinity, and you get an unambiguous finite answer for a one-loop correction in string theory. Yeah. Yeah. Not really, because the expression you have for, I mean, yes, rho, so in Rindler, rho sub A is 1 over z e to the minus 2 pi k. It's too divergent. So if you're really doing Rindler space itself, you have actually a whole bunch of infinities. I mean, one is that actually this area is infinite. Then there's the UV divergence. And so by the time you introduce a cutoff, so it's going to depend on the cutoff, basically. There may be ways, I mean, I don't mean to be so negative about it. There probably do exist ways to impose a cutoff such that then you can actually go ahead and compute this as trace rho log rho, where you can go ahead and diagonalize. But it's not a trivial matter to do that. Yeah, which is why people usually just do the replica trick, where you don't have to diagonalize the Hamiltonian. And so maybe in that setting, I can just say, I mean, of course, this was very crude, and the interesting stuff that's going to depend. I mean, this is fine, and we learned something by doing this. But having learned that thing, of course, this is very universal. So this doesn't depend on anything about the theory, anything about the state, anything about the particular region we chose, except the area of its boundary. And so the interesting physics that's going to teach us something new is going to be in here. And so this is really what we want to compute, honestly, in some specific example. And so I'm not actually going to do those calculations in any of the cases that I'll discuss, but the most straightforward way to do the calculation is by the replica trick. And there, it's just to give you a flavor of what you're doing. In that case, you wouldn't be doing fully Rindler space. You would just be doing, some finite region. And so, but it basically amounts to the same thing, where your density matrix for the region A is computed by a Euclidean path integral, at least in the vacuum, let's say, because here I assumed that I was in the vacuum, but this can be adapted to thermal states easily. And what does this picture mean? So this picture actually computes matrix elements of this operator. and a matrix element is between two states. So you fix a wave functional, sorry, you fix a state of the field on the bottom boundary, and that's your bra. So you would have like phi1 of x, rho sub a, phi2 of x, okay? And you put phi1 of x on the bottom boundary, and you put phi2 of x on the top boundary, and then you compute the path integral with those boundary conditions. And to compute trace rho squared, you take two copies and glue them together, okay? And so you just get a two-sheeted Euclidean spacetime with a conical singularity on your entangling surface. And now your job is to compute that partition function. I mean, that Euclidean path integral on this particular manifold, okay? And if you can do that, then you've computed the second Renyi entropy. And if you can do it for any number of sheets, then you've computed trace rho to the alpha for all integer alpha, 2, 3, 4, up to infinity. And then if you can analytically continue that in alpha and take alpha to 1, then you've learned the entanglement entropy. So it's a very, I mean, it's not particularly easy to do, and there are very few cases where you can really do the full calculation to the bitter end and just completely learn what S of A is. There's actually very, very few cases like that. Right, so let me just leave that at that. So that's the replica trick, and I just bring it up because if you read the literature on this subject, you'll see a lot of, multi-sheeted spacetimes, and that's where that comes from. Okay. Somebody asked about quantum gravity, and so let me make a comment about that. Historically, I mean, it's quite fascinating, actually, how this subject got started. It got started from people trying to understand black hole entropy. And Bekenstein and Hawking, through a story that you probably know something about, discovered a formula for black hole entropy. I can't write S without writing of A. So anyway, of a black hole is the area of the horizon in units of, in Planck units. So this is 4 L Planck to the D minus 1, which is equal to 4 G Newton H bar. They discovered this through a combination of understanding the classical mechanics of black holes and an analogy between the classical mechanics of black holes and the laws of thermodynamics, and then thinking hard about what happens to the area of the horizon when you throw something into a black hole, and figured out this relation, which is kind of the first quantum gravity formula ever, because it's quantum gravity because it has Newton's constant and H bar in the same formula. And this formula is amazing in so many different ways, but it's also surprising in a way that the volume, that the entropy is not extensive with the volume as it is normally with thermodynamic systems. And so that led to a lot of puzzlement. And one way of tackling this issue was just to think about the behavior of quantum fields in a black hole background, which was the way actually that Hawking finally fixed the coefficient here. Basically, Hawking fixed the coefficient by he measured the temperature of the black hole by sticking a thermometer in the black hole. So the same way you measure if you're baking a turkey and you want to know whether it's done, you stick a thermometer in it. So he stuck a thermometer in the black hole, and the thermometer he stuck in was just a quantum field. And because he knew that it was a calibrated thermometer, he knew that if the scalar field behaves in a certain way, then it's at a given temperature, and he knew that relation. So that was his calibration. So so then people said, well, let's think more about quantum fields in the background of this black hole. And they discovered this area law. And they said, whoa, that looks a lot like the Bekenstein-Hawking formula. And that led to actually a certain amount of confusion at first, because there was a question of whether maybe they're the same thing, where you choose for your cutoff the Planck length. And that's actually not a great way to think about it. But there is a relation between the two, which is that the black hole has this intrinsic entropy, which is due to quantum gravity facts. It's actually non-perturbative quantum gravity facts. And then there's also an entropy due to the quantum fields. Okay, so you should really add them up. So really, this thing has, this is the entropy of the fields, let's say, okay? And this thing together is called the generalized entropy. So what is a generalized entropy? If you have a gravitational theory and you take a region of space, the generalized entropy is the entropy plus the area of the boundary of that region, okay? And this we know is approximately given by the area of that boundary in units of the cutoff. So we have these two terms, I mean, plus a lot of other stuff. But I'm just talking about the leading area term, okay? So we have these two terms that actually look the same because it's across the horizon, so it's really the area of the horizon. So my region here is the interior of the black hole, or in a two-sided black hole, it's the other side. So this is obviously quite interesting. Might look a little bit weird at first. So what's going on? How should we think about these two terms? So first of all, we're doing quantum gravity, so we got to be careful. So we know that things go haywire at the Planck length, if not before, okay? So I haven't said much about this quantum gravity theory, so we don't really know too much about it, but one thing you know about any quantum gravity theory is that if you look at distance scales comparable to the Planck length or smaller, it's not a regular space-time, okay? In any given quantum gravity theory, like string theory, things may go haywire at much larger scales. But certainly, by the time you get down to the Planck length, you do not have a smooth background or anything like that.
Can I ask
as a question?
Yes. Where is the gravity quantized here? I mean, it's some fixed background you're working with, right?
No, now I'm doing quantum gravity.
Oh.
Yeah.
This formula that you wrote, actually, the Bekenstein-Hawking or generalized entropy formula, it's for a fixed background, right?
No, it has a G Newton in it.
Yeah, okay.
So it's for, so in this board, I'm doing quantum gravity. On this board, I'm doing quantum gravity. On the other boards, I've been doing quantum fields on a fixed background.
Quantum gravity in the sense that you're about to say perhaps that G Newton is cutoff dependent in that sense?
So yeah, but that's only on this board. So yeah, just to clarify, so I hope I didn't confuse the hell out of everybody. I just suddenly started talking about quantum gravity. Nothing I said before everything before was just quantum fields on a fixed background with a cutoff. epsilon. But the thing is that when you do quantum gravity, you have quantum fields in addition to your fluctuating spacetime. And those quantum fields also contribute to the entropy of a black hole. And so I added them up. I just took the term that Bekenstein and Hawking derived just by considering the thermodynamics of black holes. And I added to it a term that does not have a G Newton in it, that depends on the quantum fields. So for example, the coefficient here will depend on how many light quantum fields I have and other details of the theory. Does that answer your question, Spenta? No.
We can discuss after.
Okay, so let me proceed and maybe I'll answer it or maybe I'll just make the situation worse. So far things look pretty confusing because this term, let me just rewrite this thing because it got so messy.
Matt, in that, when you talk of all fields, you also mean gravitons, right?
Right, so that's included in here.
Yeah.
Yeah. So now I'm going to set h bar to 1 since I've been setting h bar to 1 in the rest of the things. So the only reason I wrote the h bar here is to emphasize that this part is quantum gravity, so I wanted to write the h bar. Okay. So this seems unsatisfactory because what the hell is epsilon? So you see there's a difference here with the case where maybe I'm a condensed matter physicist and I have some block of material and I imagine a boundary region. And then I'm okay that my entropy depends on the cutoff. The cutoff maybe is the atomic spacing or something like that, and it should depend on the cutoff. Now I have a black hole. It has an entropy. We think it has a finite entropy. Okay, it's an object. We're not interested in, we don't think objects in the universe have an infinite entropy. So it has a finite entropy. And yet when I worked so hard to calculate that entropy, I found that it depends on some cutoff scale. And that I just put in by hand. So, so that seems very unsatisfying. But to resolve that, you have to remember, first of all, that to make sense of this, I need to be doing quantum field theory on a fixed background, at least approximately. For that to be true, my cutoff has to be much larger than the Planck length. For the second term to make sense. Okay, that's one thing. The second thing is that G Newton actually depends on epsilon. And the reason is because of basically loop corrections to gravity, roughly speaking. So when you take into account loops of these quantum fields, they can generate an interaction which mimics that of gravity. And so these quantum fields actually change Newton's constant. And since they change Newton's constant will depend on what I choose for my cutoff. Because what I need is for the total gravitational effect to be independent of epsilon. Okay, because epsilon is just a parameter I put in by hand. Okay? So maybe I can be a little bit more precise here to compensate. Okay? then it turns out that the sum, so the total, turns out, this is something you have to calculate to see that it works, independent of epsilon. Okay, so in some sense, you can think of the Bekenstein-Hawking term, the first term, is a counter term. So when we do perturbative quantum field theory, we introduce a counter term, which is a term we add explicitly to the Lagrangian that depends explicitly on our cutoff, in such a way that the sum of that and whatever we get from our calculation is independent of the cutoff. Okay? And so that's exactly what's happening here, that the variation of, the explicit variation of this with the cutoff is canceling the variation of this. So if you, it's been checked at one loop, but it is presumed to be true in general. Although, I mean, things get a little bit, yeah. I'm not exactly sure what the status of that is at higher loops. Yeah.
There are some theories like n equal to 8 supergravity which are suspected to be finite, or at least it's finite at one loop. Right? So for those, I presume G Newton will not have a cutoff dependence at least at one loop, right?
I think that is not true. So there's a there's something which is sort of confusing here, which has to do with when you have fermions, because fermions in many processes, many one-loop corrections to various processes contribute negatively, and that's why you get cancellations in supersymmetric theories. But fermions have a positive entanglement entropy, and I think that their contribution to G Newton is also positive, or has the same sign as bosons. I don't think they contribute oppositely, for example, to the cosmological constant. But I think in this case, they have the same effect here, so that this is still true in the presence of fermions. And then there was a further confusion for many years about the time-like modes of gauge fields, because those seem to also contribute with the wrong sign here, because their propagator has a minus sign from the time component of the metric. And that took many years to be resolved, and then finally, taking into account gauge invariance, it turned out that the gauge fields also obey this.
I see. Then what does finiteness of n equal to 8 supergravity mean? I mean, if G Newton starts getting divergent contribution at one loop, it,
usual statement you're referring to is an on-shell statement that people just say, frankly, in a pure fraction theory, because you cannot get an R term on-shell. So the one-loop term there.
so you are saying one loop contribution can generate an R term in n equal to 8 supergravity? I see. I see. So then it's not finite. I mean, in that sense, right? I see.
Yeah.
I see. Okay. But I thought G Newton is measurable using S matrix. No?
This G Newton is as defined in the effective term you get from
Right.
the coefficient of R.
I see. Okay.
I mean, that's true even in pure gravity, right? That there's no one loop.
But if you had matter of
Yeah, yeah. Hmm. Yeah. Right. I think Ashok's question was whether you need to do a renormalization at all in n equals 8 supergravity. Yeah, there, I mean, this is.
I'm not talking about this aspect. Just take the theory and suppose I do quantum effects reaction and ask
Yeah.
whether I need to do renormalization. If I don't have to do renormalization, not this calculation, regular big theory calculation, then that's it. Whereas over here, it looks like you need to have some renormalization. But maybe the answer is that it's not true that the non-renormalizability are valid for everything.
Yeah, I mean, I think it must be the case that the G Newton, the renormalized G Newton that you use in the Bekenstein-Hawking calculation, which is the coefficient of the R term in your effective action, I mean, it must. I mean, maybe it's not a divergent renormalization, maybe, you know, but it must depend on the cutoff. Yeah, I'll try to come up with a better answer, but you know, I mean, maybe one other relevant. Yeah, I mean, okay, let me attempt one other answer, which is that these things are going to depend on, obviously, on your choice of regulator, and often something like dimreg will sweep certain divergences under the rug, which is an advantage of it for some purposes. But here we're really talking about some kind of crude regulator. So I don't want to compute this by dimreg. I mean, I don't know how to compute an entanglement entropy by dimreg. I need something which is actually a cutoff, okay? And so my guess is that with something that's actually a cutoff, even in n equals 8, you will get a dependence of G Newton on that cutoff. Even if you can then take the cutoff away and the theory remains finite and so on, nonetheless. So that you know, it may be that with something like dimreg, you kind of never see the renormalization because it's so slick. It kind of, like it gets rid of all of your power law. It just, you know, it keeps track of your log divergences and throws away all the power law divergences and so on. And it may be that it's just the very crude power law divergences that you kind of didn't care about normally that you care about now. Yes.
You mentioned the calculation by Atish and collaborators. So how did they get this formula? Because they're doing string theory, so G Newton is finite. So
Yeah, and actually it's sort of funny. It's only I mean, yeah. So they indeed get basically one single area term, which reproduces, which includes a term like this because string theory has gravity at long distances. So you kind of knew that you would reproduce the Bekenstein-Hawking term. The interesting thing is like that the one loop is that you can actually calculate this one loop contribution and so on, and get like a nice finite. Well, well-defined answer. I mean, that's a contribution to the second term. For the torus.
But they don't
Yeah.
know how to really manipulate it and get a number out of it.
Yeah, so, but this is going to come from the sphere. So this is kind of automatic in their thing. Yeah.
One
But
more
I mean,
question.
yeah, it's worth emphasizing that
Sorry.
when you do this replica trick, I got like a fifth of the way into my talk today, by the way. When you do this replica trick, the analytic continuation in this parameter is usually impossible, except in very simple cases.
Matt, just one more point which is very puzzling to me. People who do algebraic quantum field theory find a finite answer for this up to a constant. So can you throw some light what's going on?
I think maybe I'll defer that to Tom's talk. So, but maybe it's worth saying, and I assume we'll hear much more about it from him, that, I mean, he mentioned briefly at the end of his talk, you know, he had this chart of the properties that different algebras have. And he didn't include on his chart entropy, but I mean, basically, type 3 algebras don't have an entropy. And that is just the statement that if you take epsilon to 0, you get infinity. Okay, because he's working at epsilon equals 0. Whereas here, so he said that a region in semi-classical gravity is type 2, and those things do have entropies, and that's this entropy. So even if I mean, it's a little bit subtle because, of course, you don't really want to take epsilon to 0, but if you know, it basically the total doesn't depend on epsilon. So epsilon is gone once you've correctly calculated and added them up. And that is the entropy you get from his type 2 thing.
Is it really true that you said adding up? That suggests that you could do one term and another term and then add them. Don't you compute the 2 terms together?
I mean, you know, if you really are working, and that just depends on the setting where you're calculating. If you're doing string theory, which is a self-contained UV complete quantum theory of gravity, then you just compute one thing. But if you're working in effective theory, you would compute them separately and add them up. And there's nothing wrong with doing that. But it's just a calculational method. I mean, really, it's one quantity. It's only the sum is well defined.
Dot there. So in principle, there is a series in G Newton. 1 upon G Newton is the first term, then G Newton to the power 0, and then etc. So I mean, in principle, there is a computable series, right?
Yeah, but that'll start depending on the shape of your region and all of this stuff. I mean,
that you have written for this black hole entropy, can you write this as some traced rho log rho for some rho A, where A is some region inside black hole?
I mean, the idea is that is what it represents, but I don't think we have a definition of what A is in the case, you know, for a general region. Now, for a black hole, you know, when we get to holography, if we get to holography, you can actually sort of put this on much firmer conceptual ground, where you actually have 2 independent, well-defined quantum systems that are not quantum gravity, but that are dual to quantum gravity, that are in an entangled state. And then rho sub A is perfectly well-defined, and S of A is perfectly well-defined, and it's just a matter of calculating them. But in general, you would, to make it really well-defined, you have to make sure that your black hole is kind of a well-defined object in your theory.
Makes sense to add these 2 terms if that's the statement you are making, then is it well defined to add these two terms separately for black hole entropy?
Well, I think that was Finn's question. So again, writing it in this way is just a calculational method, right? Where I describe my theory in a certain way. I say I have a gravitational sector. I have quantum fields fluctuating on a background. So I think of the theory in that way. That's my choice. I put on a regulator. I calculate this. I calculate this, and I add them. But because these quantities will shift as I change epsilon, which was just my choice, such that their sum is unchanged. That indicates that physically, in the true underlying theory, there is no such separation. It's just a calculational method. No, there's also dot, dot, dots just from this. Yeah, well, yeah, not just from the graviton, but I mean, this is a non-perturbative thing, and it's going to have its own dot, dot, dot. Well, all of that stuff, even within the dot, dot, dots, should cancel. Yeah, all of the scheme dependence should cancel. If I'm really very careful, yeah. Okay.